The historical image of Florence Nightingale is defined by a lamp, the symbol of the bedside caregiver. In 1854, her primary instrument was data. She engineered a verification infrastructure to track mortality rates and sanitation patterns, forcing systemic changes in hospital care. Fast forward 172 years. Modern healthcare artificial intelligence operates on a massive scale, drawing on millions of parameters and endless racks of immense computational power. Yet, despite this computing capacity, clinical AI is repeating the error that plagued those pre-Nightingale Crimean War hospitals. It operates entirely without verifiable feedback. All that scale is effectively useless for systemic improvement if the system cannot test and correct its own work. To understand why verifiability is necessary, we have to look at how machine intelligence is actually measured. In March 2026, the ARC Prize Foundation launched ARC AGI-3, the definitive test for real machine intelligence. Previous tests asked AI to recognize static patterns. Version 3 drops the AI into a dynamic, turn-based environment with no rules. The system has to explore, form hypotheses, and adapt its behavior in real time. This chart details the stark performance divide. The best AI agent scored 12.58%. Frontier language models scored under 1%. Humans scored 100%. The Foundation's conclusion is blunt. Feeding a model more data does not create actual intelligence. Scaling up information has stalled out. Intelligence is defined by how efficiently a system learns and adapts in a novel environment, not by the sheer volume of text it has memorized. This exposes a critical architectural flaw in the current trajectory of healthcare technology. Hospitals are pouring capital into co-pilots and tools designed only to assist. Meanwhile, frontier research proves the necessity of building systems that actively learn. The catalyst for this redirection in AI research is reinforcement learning from verifiable rewards, or RLVR. This flowchart illustrates the mechanism. Systems train in environments where they can verify their answers against absolute reality, like a math problem or compiling code. This objective testing forces reasoning. Every verified cycle compounds accuracy, a feat raw data scaling cannot achieve. Compare this to the reality of the healthcare tech stack, specifically tools like ambient listening and clinical summarization. This linear pathway shows a standard clinical co-pilot listening to a patient encounter, generating a summary, and dropping that text straight into the electronic health record database. The process stops there. Documentation is a non-verifiable domain. There is no automated test suite. Because clinical medicine lacks a real-time objective compiler that can score a text summary as definitively correct or incorrect, the AI receives zero reward signal. Over the long term, this structural omission severely limits hospital operations. Without a verifiable feedback loop, a co-pilot deployed today cannot learn from its mistakes. 5 years from now, it will possess the exact same level of intelligence it has right now, stalling any compounding return on the enterprise investment. Health systems have a second option. They must mandate verifiable care environments where AI outputs are tested directly against clinical outcomes. This requires structural verification, which operates entirely differently from a clinician simply giving a subjective thumbs up to a generated note. This logic loop tracks a medication reconciliation AI agent. The AI scans patient history, proposes a medication list, and pushes it to a pharmacist. When the pharmacist manually corrects a dosage, that action flows backward as a definitive training signal, directly updating the model. We can apply this architecture to more complex workflows, like an AI tool designed for hospital discharge planning. On this timeline, we track the AI's proposed care plan over a 30-day window, ending at a strict Boolean data gate. Did the patient readmit? That metric acts like the RLVR math compiler, sending an objective reward straight back to the model, closing the loop. Right now, hospitals are wasting this crucial data. Every time a nurse overrides an AI summary or flags an error in the chart, that valuable signal disappears. Capturing these corrections requires rigorous governance, complete with full audit trails and active clinical counsel oversight to ensure the data is routed correctly. A human clinician correcting a machine is not a failure of the software. That correction is the essential fuel the model requires to adapt. Deploying these loops introduces operational risk. Workflows carry different clinical stakes, requiring a structured approach to oversight. This three-tier risk matrix dictates AI autonomy. The green tier covers low-risk automated processes, like scheduling, requiring minimal human audit. The red tier contains high-stakes clinical decisions, like a sepsis prediction model. Here, a mandatory human override gate is permanently locked in place. In these red-tier workflows, the AI is allowed to coordinate context, assemble charts, and flag anomalies, but it is structurally barred from acting independently. The uncompromising rule of clinical AI architecture is this: agents propose, humans approve. There are no exceptions. Robust governance does not slow down deployment. It provides the structural safety net required to scale these agentic models across a health system. Frontier AI researchers are currently spending billions attempting to build goal-directed, feedback-driven systems from scratch. Yet healthcare already possesses this exact operational system. It is natively built into the largest clinical workforce on the planet. This comparison shows the core tenets of the nursing profession. The RLVR circuit follows 4 steps: observe, reason, act, reward. The standard nursing process follows assess, plan, intervene, evaluate. Nurses operate as continuous, adaptive verification loops under uncertainty. The structural parity is exact. This reality makes some executives uncomfortable. The teams usually tasked with leading AI deployment, computer science, informatics, and vendor representatives, are not equipped to align this specific clinical architecture. Nursing must govern this integration. They are the only professionals who deeply understand how to measure, adapt, and track care goals at the bedside level. Nightingale built the data verification system that turned clinical observations into measurable outcomes, using that infrastructure to drive systemic change. The future of clinical AI will not be won by purchasing larger datasets. It will be won by health systems that architect their AI exclusively around nurse-led verification.